Good afternoon, young people. Here I am trying to do this again. I know you've heard this story already, but I'm going to try to record these notes one more time and see if this works. So today we're talking about solution stoichiometry. Some of it's review, some of it's not, and so we'll figure out what to do next. So the first thing we want to talk about is, what is a solution? A solution is a homogeneous mixture. It's made up of two parts. The first part is the solute. That's the thing being dissolved. It's usually also the smallest portion. Okay, the solvent is the larger portion. Okay, so it's the thing doing the dissolving. So when we look over here, what we see this crystal. We don't know if it's sugar or if it's salt, but that is the solute. And the water, the liquid, is the solvent. And typically that's what we see in our class, and that's what we do. So let's learn a little more vocabulary about this. What affects dissolving? Well, it's the nature of the solute affects dissolving. Is it ionic or covalent? Meaning, is it a strong or a weak electrolyte? Sometimes we need to know that. And ionic compounds can be strong or weak electrolytes. Is it soluble or insoluble? That means, does it dissolve or does it not dissolve? What's happening there in terms of energies and what's going on there? And now we need to know more about the solvent. So we talked about the nature of the solute. How about the nature of the solvent? Well, how much of the solvent is there? Because the more solvent, the more we can dissolve. Even for things that are insoluble, more can go in if we have more solvent to start with. The temperature is important because the higher the temperature, the more we can get to go in there, and that's something that we've proven before. The type of solvent, so we call solutions that are aqueous, they're solutions made from water. So when we say that we have aqueous sodium chloride, that means I have a solution of sodium chloride that's been, I'm sorry, I missed a U, that's been dissolved in water. So that is what we have going on there. But we can have another type of solution. A solution that we used to use when I was a kid all the time was called tincture of iodine. It was basically iodine dissolved in alcohol. So when you have a tincture, alcohol is the solvent instead of water being the solvent. And sometimes alcohol is really important because alcohol, although it is slightly polar, it can help some of those nonpolar substances to dissolve a little bit as well. So that's kind of our discussion of the vocabulary of solutions. So then when we look at water, water is known as the universal solvent for us. Why? Because water has some specific properties. High specific heat. High heat of vaporization, meaning specific heat, meaning that it can take a lot of heat and hold it and retain it. High heat of vaporization, meaning that it doesn't vaporize very quickly, so it's got a higher heat to take in order for it to get to be a gas. High cohesive forces, this is what makes the surface tension. Because the cohesion keeps it together, it has a high surface tension. And then adhesive forces, it wants to stick to other things. So this is why we form menisci with aqueous solutions. The bonds have a role to play too, because there are two OH bonds. Both of those bonds are covalent because the O has a higher electronegativity than the H. Therefore, the electrons that would be shared between the H and the O are going to actually be unevenly shared, and they're going to spend more time over here and less time over here. So that creates a partial charge, and we show that by this Greek letter over here called a delta. This Greek letter right there, the delta. So what we see here, we see this delta positive and a delta negative, and then we see this 2 delta negative. Well, why is it 2? Well, it's pretty simple. We've got a 2 delta positive over here, so this is going to have to be evened out because there is no charge. These aren't actually charged particles, which is why we have the delta. It's showing a semblance of charge because the electrons are being unevenly shared. The oxygen's keeping them more. So the unequal charge distribution makes this compound polar. It's not charged, it's just polar because there's an uneven distribution. Okay, so the bond angle is even affected because we have these 2 extra lone pair of electrons. So the lone pair of electrons need as much room as a bonding pair. So this bond should be 109.5, but because of these two lone pairs, it's squeezing these hydrogens closer together and taking away 4.5 degrees from the normal bond angle that we should see from a bent structure like this. Okay, and that is because of the two unpaired share of electrons, and we also have this delta charge because there are more electrons over here by the oxygen than the hydrogen. Okay, hydration. Hydration is simply the process, the chemical process where water is dissolving something. So since opposites attract, we have the positive end of water attracted to the negative end of an ionic crystal structure. So if you think about an ionic crystal structure, that crystal structure is made up of little pieces of ions, some positive, some negative. Well, the positive end of the water, the hydrogen end of the water, is attracted to that negative piece that's in that ionic crystal. And so that the negative end of water, the oxygen, is attracted to the positive piece of the ion crystal. So what we get here is we get this side over here being attracted to the positive ion, and this side over here being attracted to the negative ion. And this is called the hydration attraction. And if the hydration attraction is greater than the attraction of this ion, the positive ion, to its negative ion, then you have something that is known as soluble. So sodium chloride is highly soluble. That means I can put sodium chloride in water and it will definitely dissolve. While silver chloride is not. It's insoluble. So why is that? And it goes back to this law of attraction here. So when the hydration attractions, when the attraction of this delta negative to this positive ion and this delta positive to this negative ion is greater than the attraction of the ion to the ion, then the compound is soluble. If it's not greater, then the compound is considered to be insoluble. But insoluble doesn't mean nothing dissolves. And so you got to get past that kind of wording there. Insoluble simply means that not enough of it dissolves to be traceable. So that's kind of where insoluble comes in there. Okay, ionic compounds are charged particles. So we have to remember that ionic compounds actually contain charged ions. They are not sharing electrons. They are actually giving away and taking other people's electrons. They have a complete full charge, not a partial charge like the water molecule. So that attraction for the ions could be weaker than the attraction for these partial charged poles. So it just really depends. So what we see here, and this is a sodium chloride molecule, the green spheres are the chlorine, the silver spheres are the sodium. And what we see happening here is we see that the hydrogens, the positive hydrogens, are being attracted to the negative chlorines, and the negative oxygens are being attracted to the sodium. So much so that we're seeing that everywhere. We're seeing that lining up everywhere all over here. Then when we go to the next picture, what we see is enough water molecules surround those ions and actually overcome the attractive force of this positive ion to that negative ion, and it begins to take that negative ion away. This process chemically is known as dissociation. Okay, dissociation just simply means that I am taking NaCl and I am breaking it apart into its ion Na and its ion Cl using the hydration attraction of water for each of these ions. That's simply spoken what it really means. So non-ionic substances don't do that. Water can still dissolve them. And I have to turn my picture off here because I'm in the way. Water can still dissolve them as long as they have something similar to water. And these compounds are very similar because they also contain OH bonds. And we've learned that OH bonds are polar. Now, in the case of alcohols and sugars, these OH bonds are not as polar as they are in water, but they're still polar. So polarity makes these molecules soluble as well in water. So what we see is we see this OH right here getting this slightly negative and slightly positive, you'll notice it's a single delta negative instead of a 2 delta negative because we only have that one oxygen. Okay, and its other pair of electrons is being shared with this carbon. So we still have 2 extra pair, but there's only 1 more electron pair that's coming in, and it doesn't have enough. So basically there's an attraction between this oxygen and that hydrogen that's slightly positive to that's slightly negative, and this is the hydration attraction that we've been talking about, the electrostatic attraction for the hydrogen and oxygen, slightly positive and slightly negative. And so that's what we see right there. Sometimes you will see it represented as a dashed line between them, sort of like an IMF would look, but that's how that happens. Sugars are the same way. When we have oses, fructose, glucose, sucrose, deoxyribose, and ribose, we know what those are, right? DNA and RNA. So we have OHs, we have OHs, and we have OHs here for deoxyribose, and ribose is the exact same thing except we have an extra H down here, OH down here, and so all these OH sites are slightly polar, meaning that sugars are really soluble in water, even more soluble than alcohols are. So these sugars, especially small chain sugars, are pretty soluble in water because of that polarity. But there are things like fats, and fats contain long carbon-hydrogen bond chains. And if you know anything about carbon-hydrogen bonds, they are non-polar. They're non-polar because there's not a very great electronegativity difference between those two. So because it's non-polar, they do not dissolve in water. Water has no way to hydrate a non-polar substance. So we use the term like dissolves like. It's a useful guide for predicting whether something is soluble or not. However, this is not an explanation for why something doesn't dissolve or it does dissolve. You have to go in to talk about and explain the electrostatic aspects of that attraction. So we have to explain the electrostatics here in order to explain why something dissolves in something. If you're talking about an ionic bond, you always have to go back to, does the hydration energy overcome the energy that causes the ions to stay together? And so those are things that we may have to make sure that we're aware of. So huge point. Solubility is really talking about the amount of stuff that dissolves, whereas ionization is the process that is happening when it dissolves. So if I take NaCl and I put it into aqueous solution, what I get is Na1 plus aqueous plus Cl1 minus aqueous. Notice I'm not mentioning the water. I'm just mentioning the ions. So this is a dissociation reaction. This reaction is known as a dissociation reaction, and every substance that is soluble, and even those that are insoluble. So for example, let me give you an example of what I'm talking about there. Okay, it's not letting me, so let me write it above here. So if I have AgCl, AgCl still dissociates, just doesn't do it very much. And so we say it does something like this. So Ag1 plus aqueous plus Cl1 minus aqueous. It just doesn't do this very much. And so we see this double arrow. It's an equilibrium arrow, and usually there's much more AgCl solid than there ever would be aqueous. So we can have that happening as well. So the nature of aqueous solutions. So the nature of aqueous solutions goes into describing what they're made of. And really it means that we have things called electrolytes. And you've heard of electrolytes because you hear that Gatorade has a lot of electrolytes. Well, electrolytes are just the substances that your body needs to function. Most substances have to be in ionic form, especially those things that are ionic. When you hear the word sodium, it's not sodium chloride, it's actually sodium ions that are floating around in your blood, causing your muscles to do what they need to do. So we have to talk about what an electrolyte means. An electrolyte is a solution that can conduct an electric current. So basically, the more ions, the more charged particles present in solution, then the greater the amount of charge there exists, the greater that it will conduct electricity. So things that are strong electrolytes are really important to us. They completely dissociate. That means they are strongly soluble. They dissociate completely. Strong acids, strong bases, and very soluble salts do this. Okay, barium chloride is an ionic salt that completely ionizes in water. HCl is a strong acid that completely dissociates into H+ ions and Cl- ions in water, while sodium hydroxide is a strong base that completely dissociates into sodium ions and hydroxide ions in water. So we see here barium chloride right here. We see barium chloride in the bottom of the container, and then when it dissolves, we see the barium ions and the chloride ions running around. Barium is the purple and chlorine is the negative, or the green. So hydrochloric acid, HCl, here's the H+ and the Cl-, and we can see that we have all of those particles. And then finally, NaOH, we see the same thing. And notice, there is no solid. There are no particles at the bottom of the container after you've finished doing what you need to do. Do you notice that there are no particles in the bottom of any one of these containers? So these are considered strong electrolytes. They release a charge and they can conduct electricity because there are charged particles in the solution. Weak electrolytes. Now, these dissociate, but not completely. Most of the time, there's only about 1% dissociation. So we have weak acids like acetic acid and weak bases like ammonia are classic examples of weak electrolytes. So basically, when we have acetic acid, here's acetic acid. If you remember, here's that group that I was talking about, that carbon double oxygen hydrogen group right there, that acidic group. And you will notice that it dissolves in water, but look at here, we don't have a whole lot going on. Only one of these right here is losing that hydrogen. All of the rest of them are retaining that hydrogen. Remember the hydrogen right here where the oxygen is? That hydrogen right there? This is the only guy losing that hydrogen, so it's the only one dissociating, so about 1% of the time. Ammonia, the same thing. Here we go. We have ammonia over here. All of these are ammonias. We have the 3 hydrogens, and then all of a sudden here, we pick up an extra hydrogen, and we become charged. Okay? Everybody got that? All right. So strong electrolytes, they ionize completely. They conduct electricity. Hey, look at that light bulb, really nice and bright. So I have a very soluble solution right there. Everything is ionized, there's no solid in the bottom, and it's going to conduct electricity. In fact, it conducts electricity very, very well. Look how bright that bulb is. Weak electrolytes, on the other hand, do not ionize completely, and they conduct electricity weakly. So you'll notice, here we go, but look at how less bright that light is than the one that we just saw. And you will also notice down here at the bottom, it looks like there might be a little bit of solid down there. Non-electrolytes, now these are things that will not conduct electricity. So when we're talking about electrolytes, we're talking about ionic bonds. So things that are completely soluble are going to be strong electrolytes, things that are slightly soluble are going to be weak electrolytes, and things that are not soluble are going to be non-electrolytes. So they do not ionize. They do not conduct electricity. So we see here that there is no light on the bulb. We see nothing going on there. So these guys do not conduct electricity. These solutions were dissolved. We don't make any ions, and if we don't make any ions, then we have no electricity to conduct. So pure water doesn't conduct electricity. Sugar solutions don't. Alcohol solutions, antifreeze doesn't. And starches don't. All because they are not forming charged particles. They are simply dissolving because of the OH groups in the case of the sugars, okay? In ethanol, it's the OH group again that causes it to dissolve. And here we've got a bunch of sugars hooked together, and so we have these OH groups that are causing it to dissolve. But, you know, we're not talking about anything that is going to create a charge. So Arrhenius was the first to identify that solutions have conductive properties. And he said that the extent to which the solution can conduct electricity depends upon the number of ions present. So clearly, if there are no ions present, there's no electricity. If there are a huge number of ions present, then you're going to light a bulb for days. Okay, so chemical reactions often take place when two solutions are mixed. So to perform these kind of calculations, two things must be known. You have to know the nature of the reaction, and what the substance is, and the amount of chemical moles present in the solution. Molarity is our favorite unit of concentration, so you'll see the words molarity often. It is going to be something that you should get used to, and molarity literally means moles of solute per liters of solution. Molarity is a concentration unit of moles per liter, also signified by a capital M, okay? So when I see this capital M, it means the same thing as saying these brackets. When I say these brackets, I'm saying molarity. When I say the brackets, I'm saying molarity. When I'm saying M, I'm saying the brackets. It's the same thing. So that means there are 0.75 moles of sodium chloride in every 1 liter of solution. So the square brackets also indicate that it's what is inside the solution. So the substance inside the brackets is always the solute. It's never the solvent. Okay, and we always express solutions in terms of the solute, not the solvent. Okay, so you can use either brackets or the unit molarity to express units of molarity. We use molarity when we're just doing regular old stoichiometry. We use brackets in other places at other times that you'll see. Okay? So, calculations. Calculate the molarity of a solution prepared by dissolving 1.15 grams of sodium hydroxide in enough water to make 1.5 liters of solution. So the first thing we have to do is where we always have to start. We always have to start with 11.5 grams of NaOH, okay? But before we can get molarity, which is what we're looking for, we have to have moles. So the first step is always the same step that we always have. We want to change grams of NaOH to moles of NaOH. Okay, we add it up. So we have 22.99, we have 1.008, we have 16, okay, and we get 89993. So we get 39.998 grams, okay, over 1 mole. And then we do some calculations. When we get that calculation, hang on just a second. When we get that calculation, what we get is we get that we have 0.288 moles, sorry, wrong unit. Let me go ahead and cancel that out. Oops, I'm pressing buttons I don't want to press. Okay, that should be moles of NaOH. So now I'm not quite finished because I wanted molarity. Well, molarity just means, okay, I take that many moles and I divide by the number of liters that I have. I have 1.5, and I end up with a molarity of 0.192 molar NaOH. Okay, notice I kept 3 sig figs. Why? Because I had 3 sig figs right over here. So let's try another one. So calculate the molarity of a solution prepared by dissolving 1.56 grams of aqueous HCl in enough water to make 26.8 milliliters of solution. So first place we start, 1.56 grams of HCl. Okay, and we're going to change grams to moles because we want molarity. So we have to get moles of HCl from grams of HCl. Okay, grams of HCl, that's 1 in 35, so that's 36.458 grams of HCl over 1 mole, and I end up with an answer of 0.0428 moles of HCl. But I'm not quite done because I need molarity. Molarity means I have to divide by volume, and the volume has to be in unit of liters. So milli, if I do kings have dungeons under dark castle moats, milli is here. I'm going to go 1, 2, 3. So 1, 2, 3. I put a placeholder, so I have 0.0268 liters. And I figure out that the answer is 1.60 molar HCl. Pretty concentrated hydrochloric acid, actually. Okay. Let's try this. Give the concentration of each type of ion, and this is where we had a little problem on our test because we weren't sure about ions. So if I look at this formula, the number of particles is determined. I have 1 cobalt and I have 2 nitrates. So that means I have cobalt with a 2 plus, and I have 2 NO3 minus groups. Well, if the solution is 0.5, then I take 1 times 0.5 molar for the concentration of the cobalt, which means that the cobalt is 0.50 molar CO2 plus. But down here for the nitrate, I have 2 of them, so I have to multiply it by 2. So I'm going to end up getting 1 molar NO3 ions. Okay, so if we try the one here, what are we going to get? Okay, so we have 1 Fe3 plus. We have ClO4 1 minus. How many of them are there? There are 3. That's right. So we take 1 times 1, and we get 1 molar Fe3 plus, and we take 1 times 3, and we get 3 molar perchlorate. Okay, pretty simple. We're just using the formula. The formula is telling me how many of each of these species ions there are. So we don't have to panic. And notice I didn't break up the Cl and the O. They're together. They're called chlorate. Okay, so always remember and never forget that concentration, molarity, times volume is equal to moles. So the number of moles is equal to molarity times liters of solution. Now, I don't forget that, because if I start out with 10 liters of solution and I want to know how many moles of stuff, I'm going to use molarity, the number of moles divided by the liters. Liters cancel out, and I'm going to get number of moles. So it kind of makes sense that this equation is the way it is. So calculate the number of moles of Cl1 minus ions in 1.75 liters of 1 times 10 to the third molar ZnCl2. So where are we starting? We're starting with our given. Our given is right here. So we start with 1.75 liters. That's a good unit to start with. But we need number of moles. So we're going to start out with our molarity. So we have 1.0 times 10 to the negative third molar ZnCl2 over 1 liter of ZnCl2. Okay, so liters cancel out. There we go. So now we have that should be molarity, that should be moles. Okay, so now we need to know the number of chloride ions in zinc chloride. So there's 2 moles of chloride ions for every 1 mole of ZnCl2. Why? Because there's a 2 right here. This 2 tells me that there are 2 chloride ions. So moles of ZnCl2 are gone, and our answer becomes, hang on, I got to move page. Our answer becomes 0.0035 liters of Cl1 minus. No, I'm sorry. That's moles. That's not liters. Ms. Rains has got her stuff all jacked up. So that's moles of Cl1 minus, and that's our answer. Okay, that's our answer. Okay? So, typical blood serum is about 0.14 molar sodium chloride. What volume of blood contains 0.1 milligram of NaCl? So, hey, we're starting with our given, 0.10 milligrams. Okay, the first thing that we have to do is change from milligrams to grams. There are 1,000 milligrams in 1 gram. So I see milligrams are gone of NaCl. Now I have grams. I'm going to take, let's see, that is 58.44 grams of NaCl over 1 mole of NaCl. Okay, so we've got rid of grams of NaCl now. We have moles. Now we know that we have 0.14 moles of NaCl in 1 liter of NaCl. So moles are gone now. So now I'm doing 1 divided by 1,000 divided by 58.44 divided by 1.14 0.14, and we get an answer of 1.2 times 10 to the negative fourth liters, or to express that a little differently so we understand that, it's 0.12 milliliters. Quite a small quantity, actually. A very small quantity of sodium chloride. So, preparing a standard solution, it's really, really simple. We're going to use a volumetric flask. A volumetric flask because it's an exact volume of solution. So we're going to be practicing using volumetric flasks in our first lab and doing some things with that actually in our second lab. So we're going to take an amount of solute and we're going to put it into the volumetric flask. Then we're going to put some distilled water in it and we're going to swirl it around until all the water is dissolved. Once all the water is dissolved, then we're going to add water until we get to, swirl, we're going to swirl, stopper, swirl, swirl, swirl. Then we're going to add water until it gets to the water mark. Once you get it to the water mark, you put the top back on it and invert it several times to make sure that the solution is completely even throughout. So it's really not hard. Okay, so to analyze the alcohol content of certain wine, a chemist needs 1 liter of an aqueous 0.200 molar potassium dichromate solution. How much solid potassium dichromate must be weighed out to make this solution? So I need 1 liter. That's my starting point, 1 liter. And I need it to be 0.200 moles of potassium dichromate over 1 liter. Okay? So how much solid? We're not there yet, but we're close because now we have moles of potassium dichromate. The liters are gone. We can take 1 mole of potassium dichromate and divide it or multiply it by the mass of potassium dichromate, which is 294.18 grams per mole. That's from the periodic table. No big deal. Everything is the same as all we've done. It's just more stoichiometry. Moles are gone now, and if I multiply 1 by 0.2 and multiply by 294, I get 58.8 grams of potassium dichromate. Pretty simple, okay? So, dilution formula. We've already done this. This was so frustrating to me because if we're preparing a solution from another solution, we have to know what's happening. So we have a molarity. We know a volume that we're taking. We know the volume that we're making, so we know the new molarity by doing the calculation. It's pretty simple. So how do we do this? Well, we usually use a pipette because pipettes deliver volumes very accurately. We can use a graduated cylinder, but graduated cylinders have a little mess up here and there. So we use a graduated or measuring or transfer pipette. That's this one right here. That's a graduated or transfer pipette. And this is a volumetric pipette, okay? Volumetric pipettes deliver only a single amount, whereas transfer pipettes can deliver multiple different amounts. So to know which device to use, you have to know how much volume of solution you're going to need and how much you're going to be able to use there. So you're basically do the same thing that you did with the other kind of solution that was a solid solute going in, and what you're going to do is you're going to measure out how much you need, and you're going to use your pipette to transfer that into a new clean dry volumetric flask. Once you've done transferring from a stock solution into the volumetric flask, then you're going to take that solution and you're going to fill it with water to the mark. Once you get it up there, then you have this blue solution, and you should be able to figure out, based upon the fact that you knew what the volume of number 1 was, and you knew what the molarity of number 1 was, you should be able to now know you knew what the volume was going in there, and now you can know the molarity. You can find that now, okay? So, exercise 7, what volume of 16 molar sulfuric acid must be used to prepare 1.5 liters of a 10 molar H2SO4 solution? So basically, I know that my original solution had a molarity of 16 molar. What I don't know is what my initial volume is. But I do know that I am making a 0.1 molar solution, and I'm making 1.5 liters of that solution. So when it comes down to it, volume 1 is going to be 0.10 molar times 1.5 liters over 16 molar. So notice the molarity cancels out, leaving behind liters. And so I basically get an answer of, hang on, I'm looking for the calculator that I can't find on my desk. So I'm basically going to get all right, I'll let you solve that one. So I think we're going to end here. That's it. All right, thank you very much.